recall that we have been discussing about basics of fluorescence spectroscopy, and then we discussed about the instrumentation part of fluorescence spectroscopy, and then the light sources that is generally used in photophysical and photochemical experimentation and instrumentation. Today, as a part of that instrumentation components, we are trying to look at the wavelength selection optics. So where we will focus ourselves on the filters, monochromators and gratings. This will be a very good learning because a lot of technical details are there. Those who want to really start a research or learn further into the basics of the wavelength selection, it will be a nice exercise. Now, we already mentioned about the filters when we discussed about the instrumentation components, and we also mentioned about monochromators. We'll go to the details of the filters, more filters, as well as the now this filters, if you look at it, now we already discussed about the bandpass filters. Now bandpass filters, if you look at this left side picture, you can have these bandpass filters based on their absorption characteristics. It can be circular or a rectangular or a square geometry, and different dimensions are available. So you can have a band of light is being transmitted. This is basically an axis of transmission, and you see here is the y-axis is the percentage transmission, and this is your x-axis is the wavelength. Now, if you have a transmission in a particular band, you call them as a band pass filters. You always define this band pass in terms of the wavelength, which is called as the full width of maximum. So you find out the total height, and half of that height, if you find out what is the wavelength of the light that you are getting, it is called as the full width of maximum. This is the general nomenclature or naming they follow it to define the what is the small bandwidth or a bandwidth of the light that you get it. So you make a plot of the transmission versus absorbance and see the characteristics of the filter. So you have the filters available for different wavelengths. If you want to select a wavelength or a cut off certain wavelengths, so it is possible with these filters. So it is available as a narrow filters or a little broader filter also. Maybe they have 5 nanometer filters or the 20 nanometer filters. So all available based on the requirement. One has to look at what kind of filters you want it. The other family is the long pass filter. Again, it is a glass material, and it can cut off or cut on. This is what you call as a long pass filter. So one region it may allow it. For example, here I have a cut on side. That means it has the transmission only after a certain, this is the wavelength you say that this is a cut on wavelength. Beyond this it allows, it is called as a cut on. Prior to this it cuts off, and later to that is called allowing the light. It's called as a specified wavelength cut on filter. So this is also available. This also we discussed about this in the instrumentation part. And you can have the short pass filters. That means you can also call it as a cut off filters. And earlier regions it allows, it's called as a short pass. Long pass is a long wavelength allows it. Short pass is a short wavelength allowing it. So you generally call them as a cut off filter also. There are two nomenclature or jargon they use it. But I think convenient one is the long pass and short pass. It is easily matching with your wavelength that you are using it. Now this is a short pass filter where it transmits in a shorter wavelength, longer wavelength it cuts off. So this is the way you can see that the filters are available. So you can look at these suppliers or instrumentation part. where you can have the variety of filters available in the different wavelength regions. And the one you are going to learn is a new one is a dichroic filter. So this is something like you don't normally use it in a fluorescence spectroscopy, but probably use this in a fluorescence microscopy or when you go for the lasers. They are called as the dichroic filters. The name itself tells you di means two, chroic means color, dichroic. Two colors they are able to separate. Now this is basically a thin film filters, the interference based filters. Now you can have the layers of materials where if you have a two wavelengths are pass through this, and if you put it at an angle of 45 degrees, you will get the one light reflected back, one other light is transmitted. This is what is something special, you can see it. So it reflects one wavelength of light, it transmits the other wavelength of light. For example, when you use a laser wavelength, multi-line laser wavelength, you can separate the wavelengths and use it for the application. This is something new we are learning now, dichroic filters. So what is basically dichroic? It's a thin film filters, or it is an interference filter, and you can very selectively or accurately separate the wavelengths of the light from the light sources that you are using it. Now it is a thin film interference principle. It works. It is something like a small oil on the surface of the water. If you put it, you will see the color that is coming up. So what color you see, basically it is reflecting it, and rest of them it is transmitting. That is the logic behind this. This is the philosophy with which they started making the dichroic filters. You have a thin film, and you can also say that what wavelength it will reflect, what wavelength. The reflection you can see it on the color of the filter itself. Suppose if you are seeing a reflection for 532 nanometer, you will see it's a green in color. If it is for other wavelengths, let's say blue region, it will appear blue in color. That's the way it will reflect, and then it will transmit. So it's a very selective filters for a specific job of separating the beam path of the two light sources that you are using it. That is what is called the dichroic filter. Now, what are the application if you generally see it, if you use it for a beam splitting applications? The beam splitting is if you have two wavelengths and split them up separately, the separation of the light wavelengths that is possible. So you always use it as a 45-degree angle reflective mode. And you can also put it like an additive subtractive color filters. You can have the separation of a blue, green, cyan, yellow, magenta, orange. All these colors are possible. And you can make it like a trimming action, like your long pass filter. You can also use it like a long pass filter if someone wants to use it. You can also use it like a short pass filter if you want to use it. It all depends on what wavelength you want to select it. And you can also think of using it as like a band pass filter. So the dichroic is something interesting. Two color, separation of two color, that's the logic behind it. Sometimes you can also use it like a notch filters. You have a, for example, Raman spectroscopy and all that. You can use this as a notch filter also. It's a minus filter. So this is the way you can see that the filters, these dichroic filters, find application in the real world. If you see it, how exactly one uses it. Suppose if I have a laser source, let us assume it, I have a laser of ND-OG laser, and ND-OG gives you fundamental of 1064. The laser is the 1064 nanometer. And then when you generate 1064, I can also do a frequency doubling that we'll slowly learn. We will use the nonlinear optic phenomenon, generate the other wavelengths also. Let us say we are generating a green light along with 1064. Now I want to separate the green light, right, after passing through the frequency doubler. I want to separate it. You can see that if you put a dichroic separator, this is what is called as they are very specific. I have to use the 532 nanometer dichroic separator. So you will see that the green light is reflected and red light is getting transmitted. This is where you will find dichroic filters finding application to separate the two wavelengths. It may not be 100%, at least you will see 99.5% or 99%. there will be some amount of green also will be passing through it. So it is not possible to achieve 100%. You can also see that certain amount of red is also coming along with the green light. Again, you can put one more filter, dichroic filter. You can improve the purity of the laser line. You can put one more here, deflected here, and then you will allow the red line 1064. You can get a the purity of the green can be improved by combination of a two dichroic also. So at the 45 reflection orientation, this is the logic, or this is the application. You will see it when you go for the dichroic filters. So the meaning itself is two color filters. So we have all seen these general filters. I'm just summarizing it here. And you have a broad bandpass filters. We have a narrow interference filters. We also have one more filter called as a neutral density filter. This is basically a attenuator for the light intensity. You generally use it for many applications, including the quantum male determination and so on. Wherever you want to cut down the light intensity, it is possible to have the ND filters. So a ND filter is something like you can use even a thin layer of filter papers or the lens cleaning tissues. It is like a grid mechanism. Otherwise, you can have a small layers of a coating with the small thickness, so that will help you to work like a ND filters. Let us see some examples and how they look like. And before going into that, we can also use these filters. For example, band pass filters. Let us say I'm setting up a fluorimeter or a Raman spectrometer. You can see that the filters, for example, if I want to take a laser line to the sample, I don't want anything longer than the laser line entering into it. So I can have the laser line band pass filter. It will allow only laser line. And suppose if I'm measuring a Raman or a fluorescence signal, they're always longer than the excitation source. So let us say you put a laser line long pass filter, it will cut the laser line, it will allow only the other signal. So that's the way you can use this combination of two filters, long pass filters also. One for the band pass for the laser, the other for the cutting of the laser line. So that's the way you can think of combine the filters and select the light that you wanted for your experimentation. This is the logic of the usage of filters. Now, if you look at the other family of filters, it is also called as the AOTF. It is something special class of the filter, which is something based on the variation of the refractive index within the material. So how do we vary the refractive index is give an RF signal, is the radio frequency signal to the sample. So you have a tunability. It's basically a tunable filter. So far we have seen a fixed wavelength, right? Now you can tune the wavelength of the filtration. That is possible. So this is simply based on the refractive index that creates it by supplying an RF source to the material. And you can see that one wavelength will diffract in a different direction, the other one will reach your material that you want to do it. So this is possible to tune this crystal. So this is basically a acoustic optic tunable filters, otherwise you call them as the AOTF. This is something a special class. As you learn the dichroic, here is a multi-line. One filter can really work like a multiple laser lines also. Only thing is you have to give a different RF frequencies. So you will see that the different way refractive index is set in the material, and you will select the wavelength. This is another interesting filter, and they're all based on the ACOUSTO. You can also do a electro-optic modulation, that is also possible. So EOM principles and AOM principles, they use it. So mostly for filters, they use the AOM principle. Maybe for the attenuation of the intensity of the lasers, you have the possibility of using a AOM as well as the EOM. But filtering action, mostly they go for acoustic optic tunable filter. So this is something interesting class, and you will find this as an application in microscopy, fluorescence microscopy. They extensively use this AOTF filter. So it is an acoustic optic tunable filter, right? So you can see that how exactly they can use it for a 3 lasers, simultaneously tune it and select it. This is using an acousto-optic tunable filters. And if you want to really do a 3-line excitation for your fluorescence imaging, you can selectively filter it using a 1 AOF filter can do the 3 purposes simultaneously. That was something interesting to look at it. This is something special filter. They are not cheaper. They have to really put a lot of money on this. Whereas in a normal glass filter, it's just a colored glass absorbing type of filters. They are all very cheaper. Here is a special class. They work for the selection of multiple wavelengths. One filter will work for the multiple wavelengths. So I was mentioning about ND filters. Those who are expert in camera, or you are those who are really photography persons, so you will see that you can have a small circular filters in front of your camera. That is basically an ND filter. ND filters are available again in different geometry. It is available in circular geometry, and you can see that the attenuation levels are varying as you see the intensity of the color of the filter. So you can see that the what is happening with the filtering action. I have given you an image also how exactly filtering is. The intensity of the color is higher and the filtering is also more. So it is available in different formats also, like a square formats, the individual glasses, or you can have it as a wheel also. So you can put it on a wheel so that you can rotate and find out, or like a disc also you can use it. Like your CD-ROM disc, you have a different zones in which you have a different gradients of the filtering level. So you can see that as you tune it, you will see the filtering level will change. So, or you can use it like a slide also, one glass plate having a different zones of the intensity. So these are all kind of a black coating they make it. It can do a filtering action. So that the grade, it is something like what we use is a gradient fill in your PowerPoint. Also, you can see it, color intensity changes. That's the logic behind this. So these are all neutral density. They do not do any other purpose. Just they attenuate the intensity of the light that you are using it. This is a very simple filter. So these are the basic class of the filters. So one has to know about it when you learn fluorescence spectroscopy or photochemistry. So you need to know about long pass, short pass, band pass filters, or you need to know about interference filters, dichroic filters, AOTF filters. Our next component in the handling of the light is the monochromator. We select the wavelength using a monochromator that we have mentioned about it when we learned the fluorescence spectroscopy instrumentation. So let us see what is inside this monochromator. So we also mentioned about the design of the monochromator was a Zerny Turner. These are the name of the person. So how they configure the grating and the mirrors, this geometry of configuration is called as the design of the Zerny and Turner. So it is named after them, in which you will see a 2 slit width. One is the entrance, other is the exit slit width. You will have one grating and 2 reflecting mirrors. So it can be curvature type of mirrors. You can use it so that you get a focus of the light. So now let us go into the details of the composition or the components of the monochromator. If you look at different forms of the monochromators are available worldwide. There are so many people manufacture monochromators. Now, if you look at inside, we have the mirrors and the grating. This one is a grating. You have the entry port, light is coming here, disperses, and then you have the another mirror reflecting it back to the other slit, exit slit. Now you can see that. Let us try to understand what is this grating itself. Grating is an important component. Many of us, we chemists, do not open the monochromator. We don't get an opportunity to work with the monochromator also, but physically we should learn about this, because when we handle the spectrometers or the monochromators, what are the features that we have, what kind of monochromatic gratings we have it, so which will suit our requirement, and how to really maintain and manage or handle the grating component. These are all interesting and important component. I thought it will be a comprehensive, and also it will give you a very good foundation, because as a chemist we don't get an opportunity. As a physicist, probably people learn about it, but anyhow, I've given you a complete exhaustive details about these monochromators and also on the grating. Now if you look at grating itself, what is basically a grating? It's a diffraction principle optical material. It's a diffraction grating. It's a collection of the reflection or the transmission. Now there are two ways you can have your grating: transmission grating. Physics people always do an experiment in their optics lab, optics practical lab, a transmission grating, and then they use a reflection grating. They study about resolution, separation of the light, all that experiment. But maybe as a chemist we don't do that, but you would have studied somewhere. But anyhow, we recall, and how do we use it in our instrumentation. So basically this diffraction grating really works you to have a dispersion of the light. White light is getting dispersed. That's what we are using it. Our purpose is to separate the wavelength of light from a white light. That is the purpose we are using it. So we have studied the prism. Prism is also one of the dispersion component, but prism has got its own limitation, whereas the grating has a much more advantageous. Even before the gratings were invented, they were using a prism based spectrometers, including Sir C.V. Raman has used a prism based mono spectrometer only. So this is the interesting component, but now you can do a better resolution by using a grating. So grating had a great history also. You have to look at the history. I'm going to mention about this, what kind of how they have evolved in the designing of the grating. What kind of, so what is this grating is basically they have a grooves. Actually they have lines drawn. They take a small glass plate, they draw the lines. It works like a diffraction, as we have studied diffraction law. So it works, lines are what diffracting the light and dispersing the light that you're using it. Now if you look at the reflection grating, it consists of a grating superimposed on a reflective surface. That's the only difference. Whereas transmission grating is without any reflection surface. That is the difference between a reflection grating and then transmission. Maybe you can use the metallic coatings or any reflecting surfaces on the grating, so it will work like a reflection grating. Without any coating, ordinary glass plate will work like a transmission grate. Only thing is you have to draw the lines. So how do we draw the lines? We'll see it. So normally, they make these gratings by making one original master, they call it, and then they make a pattern out of it from the scratch. They make it and then use it like something like a photocopy the pattern on this. This is the principle called as a holographic recording. So it is called as the holographic grating. So gratings are generally made in a two basic principle. One on a physical drawing of lines. So let us learn how they are doing it, and also you can do it with the holographic principle. So holographic principle helps you to have a recording of this. Very good, fine. It has started coming up. Fine. So if you look at in the year of 1821, Fraunhofer has done the a real contribution, and it is really made his beginning of grading works. Now if you look at the Fraunhofer, basically his contribution in physics and interference is quite high. And then in the year of 1850, if you look at it, Nobert is basically a Prussian instrument maker, and he made a gratings much superior to Fraunhofer. And about 1870, this manufacturing or making of gratings are shifted from Europe to US. So the Rutherford and New York, he was basically a lawyer actually, and a kind of an hobbyist in astronomy. He was started making the gratings, and it was the gratings that he was making it, which was much powerful than prism that was available on those days. And there are some limitations also. Next to him, Rowland is basically a professor of physics in Johns Hopkins University. He has started developing the methodology for making of gratings. They were really very good, and even he was continuing making lasers till his death also, almost like a 1901. And in 1947, that is how the commercial people were coming in. They are a company like Bosch and Lamb. The Bosch and Lamb is a well-known company which were making a lot of optical instrumentation. They decided to make the precision gratings, so which could be really made commercially, and that was a real breakthrough. They had it in the year of 1950. They could make it, and they really made these gratings based on the Michelson laboratory. Michelson is again very well known, called as a Michelson interferometer. Now, subsequently, it has taken over by commercial manufacturers, from the research to a scientist lab, and it has gone to the commercial manufacturer. And 1997, you can see a transition to the spectronic instruments. It was basically acquired by Thermo-Electron Devices. Now it is Thermo Fisher. Some of you might have heard about this Thermo Fisher Scientific. They also make chemicals in India, also Thermo Fisher Scientific. So this is a large company. They invest quite a lot of things, and then it has gone to the commercial. And in the year of 2004, Spectrophysics, which was really making it, was acquired by Newport Corporation. So even now they are the leaders. And this was the grating called as a Richardson grating. And the lab that he was calling is also very famous, well known for their grating lab. This is how the history was there in grating manufacturing or making from a small scale to a larger scale. Now, what is the physics behind this? When you have the incidence of monochromatic light, it gets diffracted into discrete directions, and give a picture. We can really get a grooves, and these grooves are really making the diffraction phenomenon happening. This is the important point to look at it, and this is based on the interference. So now if you look at it, and I've taken a grating, it is basically a grooved grating. We will discuss what kind of a grating it is. Now you can see the light of incidence and the reflection. So now you can see these angles and diffracted lights. You can see that reflected lights are diffracted on the counterclockwise, diffracted on the clockwise. So counterclockwise is given with the positive symbol, and clockwise is given a negative. It's beta -1. Here is a beta 1. So this is basically a reflection grating, and the D that you are seeing it is the spacing between the lines. So it is basically interrolling distances. That is what is like you see in a Bragg's law, D-spacing. That's the way you can look at this, so that it will make us to understand easier. Right. So now if you look at the transmission grating, exactly incidence is one side and transmission, and then you have the diffracted coming on the opposite side. This is the beta 1, this is the beta -1. So you can see that the different formats of the grating that we use it. But in a normal spectrometer, we don't use the transmission grating. We use only the reflection grating. Right. So you have to understand, from your Bragg's law, you can also have the simple mathematical expression, which is called as a grating equation. So what you get now, if I use the two parallel rays, how exactly it gets diffracted, and what is the path difference between them, and what is the d-spacing. That's the way you look at it. If you interconnect all that, and you get a expression which is called as a d sine alpha and d sine beta. It's basically a minus sign, path difference subtraction. Because the angle is negative, you put the +1 here. Sine of a negative angle becomes positive. So this is the basic equation called as the equation of grating. Now you can call them like a m lambda, which is the wavelength of the light that you are using it. D is the spacing, interline spacing, and the angles are alpha and beta. Alpha is the angle of incidence, and the beta is your diffracted angle. So that's the way you combine this, get a grating equation. Now you can refine further. D can also be taken into the left hand side, and your D by D can be replaced with your G also. So what is the G and D relationship? G is equivalent to 1 over D. That is what is called as the groove frequency. That means how many number of lines that you are drawn. It's called the groove density. This is an important parameter which decides the resolution of your grating. How it is the density of the lines that you are using it. So G is very important, which is equivalent to 1 over D. So this is the important point. And also you should understand, when you handle the grating, what is the resolving power and the spectral resolution. So ultimately what we want is the good spectrally resolved light that you are getting out of the spectrometer, otherwise monochromators. So how do we get that? Is the resolving power R is defined as R is equivalent to lambda by delta lambda. Delta lambda is the what is the separation that you can get it. So you can really see that you can depends on what, it depends on the locations on the entrance also. That is also important, entrance and exit slits. And your resolution not only depends on the R factor. When you combine the grating with your spectrometer, otherwise monochromator, so you will see that the entrance slit width, exit slit width, they also decide the resolution. But it is good to have grating also contributes in a major fashion for the resolution. So which is nothing but the ratio of the lambda by delta lambda. That is what we call it as a grating. Now looking at the ruled gratings, we already said gratings are made in two different ways. One is by drawing lines. They are called as a ruled gratings. So how do we make a ruling on the glass? Again, using a diamond tips. So you can make a real rule, and that ruling device is called as a ruling engine. It was basically a Richardson. Now the lasers that we made, ruling pattern laser, they are called as the Richardson gratings. They are basically the world well-known, renowned gratings. They made it, and that is an important contribution they gave for the grating manufacturing. Now you can see that I'm giving a picture of what kind of a machinery they used it. This is the open machinery, but it's closed one. This is called as the MITB and Richardson Gratings MITB engine. They used as an engine to draw the lines on the glass plates or a quartz plate with the coating, without the coating. With the coating, if you make it, it becomes a reflection grating. Without the coating, it becomes your transmission grating. So this is how the gratings were really manufactured and for the application. Now, if you look at this, how exactly it looks like. When you draw a line, you will see a small mechanical deformation that you see in the surface of the glass, and this is your transmission grating. Now there is no reflection coating. This is your transmission grating. When you have the reflection, it becomes your reflecting grating. So these are the two basic concepts. They make it, or two types of the grating. They make it over the ruling and grating engines, which really which draws the lines on the surface of the glass. Now there's another family called the blazed grating. So what exactly is the blazed one? Blazed one have a lot of advantages over the ruled one. So blazing is basically a triangular shaped sawtooth type of the surface grating. You will see it, and the blaze, always they blaze at a particular wavelength. It is called the blaze wavelength. They are very characteristics. The gratings are very characteristic of the blazed wavelength, and that not only the wavelength, and also it depends on the angle that it really makes it. Now what is the angle of the bracing? Now you see that, and you have it was, in the case of the ruled one, it was a plain surface and you have a small dips. Now you can see the different kind of a blazing, and you have a triangular sawtooth type of the structure. Now this is the angle that we talk about it, and these are the separation between the two lines that we call as a line D spacing or alpha, whatever they call it. Now you can have the direction of the blazing, how exactly blazing is done. This is called as a blazing direction, and this blazing direction is also important. So you have to understand what is the angle of blazing and what is the wavelength of the blazing. These are the important parameters that decides about the resolution, and then how exactly they reflect or diffract the light that you are using it. The third family is the holographic grating. So almost in the year of 1960, they started making grating based on the holographic. Again, hologram recording is also based on the interference. So they made use of the interference principle to record the grating itself. They make a polymeric material, so the coating they make it and then record the patterns, and that pattern formation is very similar to what you see on the surface of your CD player. You see the lines drawn, it really disperses the white light, you see the colorful light coming up. That is basically an interference phenomenon, and that is a principle, similar principle. You can have it on the interference pattern of recording the grating also. Now they made a holographic gratings. So holographic gratings had some problems, and they have an advantage and disadvantage also. So the principle of manufacturing based on the interference pattern on the surface of the material. So on the glass surface, they use some polymeric material and record it. And they always make a master of the holographic pattern, and then they make a copies out of it. It is something like, olden days, the printing action. Even now they make a screen printing like this, or you can have a letterpress printing, right? They make a master, and then from the master you make the holographic printing of your grating itself. So this is how they were really making the grating. And if you look at the fabrication process, if you look at the fabrication process that you look at it, now you can have the photoresist. That's what I told you, photoresist material, and then they have a substrate, make a coating, and then you can have a laser beam actions, and then you can have a holographic recording. So now you can see that holographic formation. This is possible like a circular surface or also like a triangular surface. So they also make using an ion beam methodology, and then make a copies out of it. So that is what is called the replication, duplicating it. That is the way they are making the grating. So this is, they make a master, from the master they make a copies out of it. So this is a simple way of making gratings. And now if you see the surface, how exactly it looks like. Now if you have a blazed one, it will be like this. If you have a holographic one, you will have a wavy type of the surface. So this is how you have a 3 ways of manufacturing. Otherwise it is 2 ways. Blazing, it is an additional component. You blaze at a particular wavelength, and that was given by a French group of people, and blazing was their advantages also. So when you blaze it, what really happens, and blazed gratings always offer extreme efficiencies at the design wavelength. We say blazed wavelength. At a particular wavelength that you are blazing it, it gives you a very good efficiency. But there are some problems called as the periodic errors, and such as ghosting and relatively high amounts of scattering also, you will get it. So holographic are basically designed to really avoid your errors that you see it, and this is your eliminate the errors of the ghosting and so on. So there are some drawbacks also for the holographic grating is concerned when compared to the blazed one. Blazed ones are high efficient, whereas the holographic ones are reduced efficiency. Though each one has got their own advantages and disadvantages. So based on their application, you always select your gratings. So once you have the grating done, now you have to mount it into a monochromator. That's very important. Again, a monochromator were available in a different mounting design. So that is the important one to see it. So I think so now you can have the two entrance. It's called as a litro monochromator. I think my there was a problem in my animation here. You don't worry about it. There are two ways, three ways you can combine it to have the grating into a monochromator. So in one of that is your Zerny-Turner monochromator. I told you Zerny-Turner is giving you an entrance, exit, and then you have the grating dispersion, collection of light. So that is how you have a possibility of a three way of mounting the grating into the monochromator. Out of that three methodologies, Zerny-Turner was very popular. You can also use these gratings to have the double monochromators. You can have the grating here, two gratings in one monochromator itself. That gives you a good resolution. It also avoids your stray light. So this is basically a double monochromator combination, right? So now, so far we were talking about plane surface gratings. You can also have the gratings out of the concave surfaces. So it's called as a concave gratings. You can also mount it on the monochromators. So you call them as a it is the first mount was called as a Rowland circle monochromator. So that was the one that they used it, Rowland circle. Right. The next one is basically now you can see that your curved surface is called as the Wadsworth spectrograph. So now you can see the orientation is different. Now you are collecting the light and putting it on the grating, and exit and entrance or the exit lights are there. At different orientations you can have this. The other one is called the far field spectrograph. Now you can have the wavelength separation lambda 1, lambda 2. You have an entrance slit. So it's falling on this grating. That is how you can have the grating not only on the planar surface, you can also have it on the curvature. You know, it's called as concave gratings. So that will help you to have the spectrometer design, so otherwise monochromators design. So this is normally the concave type of gratings. They always use it for a array detector. So this is a common way of using diode array spectrophotometer. If you use it, they always disperse it with your concave type of the grating that they are using it, right? So when you have made your monochromator, so some of the parameters that you have to look at it to study about, to understand about your resolution. The one is called as a F number. F number is just a numerical number which is nothing but the ratio between the focal length and the diameter of the your grating that you are using it. That is what is basically called as the F number. This is almost equivalent to a numerical aperture. You will learn numerical aperture. Probably those who have studied little bit of physics and microscopy, they know about the numerical aperture. It's a cone angle of collection. That's a numerical aperture, which really talks about the resolution in your imaging and the microscopy also. So the numerical N number is basically F number is nothing but your ratio of the focal length and then the diameter of your material or your grating that you are using it. So this is very important. F number, they always say it. Now, if you look at the monochromators, they always see the dispersion based on the number of lines that you are drawn. It's called as a groove density. This is what we mentioned as a G value. G is number of lines that you are drawing it per millimeter is called a G by G per G is basically the number of lines, 300 lines drawn per millimeter, 600 line, 1200 and so on. So as you see the increasing number, the resolution of your spectrometer or grating is better and better. The larger the number of lines, better the resolution of your spectrometer. That is what you should understand. From this, if you have a fixed focal length in a Zerny-Turner, how exactly you can improve the resolution by changing the grating with a different resolution. You can also change the resolution by combining a different slit width. I told you not only grating is deciding the resolution and also the slit width. So you can have the combination of both to have the better resolution. So this is very important. When you use a grating, you also have the problem associated with that is a scattering. Now there are two basic scattering one would come across when you use the grating. One is called the diffused scattering, and it is basically due to the roughness of the surface of the grating. And the second, in this, it's also the primary cause in the holographic grating. Diffuse grating is the basic problem that you will see in the holographic grating, and its intensity is higher near the diffraction order of lambda. This is very important. Diffuse scattering will intensity will more in the diffraction order. So this you have to be careful when you're handling the gratings. So what kind of a scattering you get, and you also have the in-plane scattering. And this is basically an unwanted energy dispersion plane. You have a lot of unwanted energy in dispersion plane. It is primarily due to the random variations in the groove space or a groove depth. It is basically the problem associated with the grating itself. Now, its scattering intensity is higher than the diffused scattered light. This is very important. So, the plane scatter will be more than the diffuse scatter. So, these are the two basic scatterings. One has to be careful when you are using a grating. Now, how do we select a grating for your monochromator is, first you should look for what is the spectral region. You go for based on the wavelength range that one can use it, and then buy the grating. Or when you buy a monochromator or spectrometer, spectrophotometer, you have to give a specification for the grating also. You should also look at the peak efficiency of the wavelength, and then the focal ratio or throughput. What is the light output that you get out of it. Resolution, as we already said, resolution, resolving power, and dispersion, how much light it disperses. And then the free spectral range also, what is the range that you use it, what kind of output optics you can have it, and the size of the grating. This is how you can decide your monochromator. So what kind of a grating you want to have it inside the monochromator. Maybe it looks a little bit technical, but you should also understand what are the bases. Unless you decide the right grating, you may not be able to see the good resolution, and you may not be able to avoid your scattering that is happening in the grating. This is very important. Now, once you have the monochromator grating decided, you can also select your monochromator, or whether you want to have the monochromator or you want to have the spectrograph also. So you have to select it. So this will really look at the what is the slit width that you have it, what kind of a slit width, the entrance slit width, and the band pass that is required, what is the precision, highest dispersion can have it. Now, largest optics of affordable, when you go for a large F number, we already said focal length is larger, and the cost is going up. You have to affordability also, you should look at it. And you also look at the groove density, G value, groove density, highest groove density to accommodate the highest spectral resolution. So these are the three basic parameters you have to look at it. And groove density, what is the focal length, and what is the dispersion. That's the three basic parameters you have to look at it, and then decide your monochromator. Then you can decide your spectral resolution. So once you have your machine available and when you are using it, important is handling of grating. It's so sensitive, you should not damage it. This is, once you damage it, you lose your spectral resolution. Not only it will have basically irreversible damage it will create. The groove profile that you are looking at it, if you physically touch it, even if you have a finger marks, can really damage the surface. So if you touch it with just a bare hand, you will see that making your finger marks that will really create the disturbance to your spectral patterns. And fundamentally is never touch the surface of the grating. That's very important. Don't touch it at all, and never allow any mount, any physical mount like a mechanical materials. You should not go closer to the surface of the monochromator, so that you don't make any scratches on it. And not only that, you are not even supposed to breathe or now you cannot, you should not even talk before the grating, or even you are not supposed to breathe before the grating surface. This is very important. Once you breathe it, so you will see the moisture condensation that will also spoil it, and then your organic matter falling on that. So you have to be very cautious when you are handling the grating. When you are really mounting it or removing it, you have to have all your finger cord gloves or a full gloves. You have to really make sure you put a mask. So all that precautions you should take. And if there are some contaminants on the surface of the grating, you can also remove it, but you must use the right organic, very spectral grade solvent. But you should not apply any physical pressure on this. So with the normal lens cleaning tissue, you should put the drop of the solvents which can remove it. But generally one should not clean the, but over years of usage you will see that there's a dust accumulation. Maybe dust accumulation you can use a mild air pump, like your pipette master that you are using, just like a balloon of the pipette master and then blow it up, so you will see the dust is going away. So that's a normal exercise of the cleaning of optics one has to do it. This is how you should look at the application of the gratings in your spectrometers, and this is what I wanted to discuss about it.